Hey, what's going on YouTube? What's up? How's it going? Welcome back to my channel, y'all. If you're new, welcome. My name is John. I am a math enthusiast. I studied math 15 plus years ago. I trained to become a professional researcher in math. And then I decided that sounds like a hard life, and instead I went into software. Now, 15 plus years later, I am trying to rebuild my passion and love for math and just study math for fun for myself. Because you know what? Math is just beautiful. Math is truly beautiful. And to me, the beginning of beautiful math is linear algebra. So for the last 40 or so days, 35-ish days, I've been practicing linear algebra almost every day here live. So it's exactly as boring as it sounds, but I'll try to make it fun here and there. I'm going to be practicing. I'm just going to be studying math. Primarily, we will be working exercises out of this book. I'm working in a breadth first way, taking the next problem, taking one problem from every section, and then restarting, and taking the next problem from every section, and then restarting. So it's our third time going through chapter 6. So we'll do a couple of problems about projections. We'll be doing a problem about the Gram-Schmidt process. For some reason, I'm on problem 4 of section 2, but only problem 3 of section 1. That doesn't seem right. Let me go back to my old notes. We have 412 pages now in this iPad. That's crazy. That's a lot. So let's find the last reset. Was it that long ago? When was the last reset? 2.3, chapter 1. We did a reset. We were in chapter... This was a review. This was my reset. Here's chapter 7. Yeah. Okay, heck yeah. So we did... Last time that we worked chapter 6... We worked 6.2.3, so that part is correct. And we worked 6.1.2. Okay, well, so this was last time that we were in chapter 6. We worked problem 2 of section 1 for some reason, and problem 3 of section 2. I don't make the rules. I don't know. A little bit confused. Oh my gosh, sorry about the white, blaring white there. Okay, so we're going to be working these exercises on projections, the Gram-Schmidt process, orthogonal matrices, and then for the first time we're going to be getting into section 4. So first I'm going to take some notes. That's going to be as boring as it sounds, but maybe for some people it might be entertaining. And then we're going to work this problem on the projection matrix. I don't know if we're going to get to section 5 today. Let's give this a big old question mark on these two. I'm not sure yet. We'll see. We'll see how my energy levels are at that point. And every now and then, if y'all want it, I could play some guitar between pieces or between exercises or something. So I am a classical guitarist, and yeah, I am proud to share these recordings that I've made as background music. So let me know if you enjoy the background music, and let's go. So, all right, 6.1.3, projections. Find the projection of this vector on each of the unit coordinate vectors in R3. That doesn't sound too bad. This sounds reasonable. I think I can do this. Okay, so from what I remember, before we look at the section or look at my previous notes or anything like that, what I remember is if I have a vector B, if I have a vector B, if I want to find the projection of a vector B on a vector V, is B dot V divided by v dot v times v. This is what I remember. I believe that this is right. And we write this as b underscore v. So this is like a decomposition of a vector. If I have a vector, if I have two vectors, then I can find the projection of one onto the other. Like this is a nice little right triangle. And then this portion is the projection of b onto this other vector v. So this portion is b v, and then this is b v perp or something. This portion, this other vector. So we have this decomposition that a vector is decomposed into its orthogonal components or something. So in our problem, our vector b is 1, 2, 1, and we are finding the projection on each of the unit coordinate vectors. What does that mean? Well, that means I'm finding the projection onto E1, which is b dot 1, 0, 0 divided by, well, let's just, here, why don't we make this simpler? E1 divided by E1 dot E1 times E1. E1 is 1, 0, 0. If you're working this problem, you probably already know that, but I also want to try to explain out loud to people who are new to this type of math, and try to give some examples and a little bit of clarification. So here, the vector b projected onto that, well, the dot product of these is 1, and E1 dot E1, it's a unit vector, so I know for sure the dot product of it with itself is 1. And then multiplied by the unit vector itself, so the projection of b onto E1 is E1. The projection onto the j component, onto the second component, thinking ahead, this is going to be 2E2. And then the projection onto the third component would be E3. So there's our answers. Maybe I could write this as BI, BJ, and BK, but IJK looks like they're indices if you ask me. It doesn't seem as clear and obvious that we're talking about the standard unit vectors. So is this an odd problem? It is an odd problem. So let's, was there anything more to the question? No. This is a nice, simple, straightforward 30-second problem for sure. Not bad, but eventually these are going to get hard. And eventually I'm going to be sweating every time that I'm working these. So we are in section, yep, easy. The book actually writes them out, so I guess I will too. 1, 0, 0, 0, 2, 0, and 0, 0, 1. May as well, but same thing. Those are just two different ways to write the same thing. Cool, done. Simple. I kind of want to do another problem because that one was like just a little too easy, I feel, but hey, not bad. It's nice to get a little warm-up problem sometimes. It's really interesting to me. At this point, studying linear algebra, I'm kind of like also thinking about the presentation of this book compared to the presentation of other books, and which exercises one author includes compared to the exercises from another author. It's cool. I want to get really good at linear algebra. So help me, y'all. Feedback is a gift. Let me know how I can get better. Does this seem like effective, deliberate practice to you all? Like this way of working? I don't know, dude. I don't know if I'm wasting my time over here. So we got 6.2.4. We've got the Graham-Schmidt process. Cool. So, oh wait, I don't have to rewrite that. I already wrote this down. Yeah, I already wrote this here. Okay. Oops. Verify that the generating set of the given subspace W is orthogonal, and find the projection of the given vector B on W. So this is a similar type of problem, right? So, solution. To see the set is orthogonal, we show that vi dot vj equals 0 for all distinct vectors in the generating set. So I'm going to label these v1, v2, and v3. v1 dot, so we just need to compute each of these dot products. v1 dot v2, v1 dot v3, and v2 dot v3. v1 dot v2 is -1, -1, +1, +1, and that's 0. v1 dot v3 is 1, -1, -1, +1, and that's 0. v2 dot v3 is -1, v2 dot v3, -1, 1, -1, 1. And that is also 0. So you know what, I've been messing with my iPad settings over here. We gotta not crop it so much. Okay, let's not crop it that much. Okay. So this part is done. And now find the projection of the given vector B on W. So for the second part, to find the projection of B on W, the projection of B on W is going to be the projection of B on V1 plus the projection of B on V2 plus the projection of B on V3 given that V1, V2, V3 is orthogonal. Is this correct? I need to remind myself about this. Does the subspace decompose in this way? Or is there... Am I missing like a coefficient or something like that? Like a norm or something on each of them? I don't think so. I think it's just this. So we've got an orthonormal basis, Gram-Schmidt process. Okay. Yeah. Well, no, this is the same. It's the same thing. If it's an orthonormal basis, equation 3, yeah. Projection using an orthogonal basis, they're just writing it all out explicitly, but it's the same. I wrote it the same way. Okay, heck yeah, I got it. So, each of these, recall that B underscore VI is projection of B on vector VI. BVI explicitly from the previous section is B dot VI divided by VI dot VI times VI. So the book writes out this equation using each of these terms separately, but it's the same thing. I prefer to think of it projection 1, projection 2, projection 3 onto each of the basis vectors. This is cleaner to me to think of the way I wrote it. Okay, so we already found that the set is orthogonal, so vi.vj is 0, so then this equation holds. So we find the projection of B on W is B dot V1 divided by V1 dot V1 times V1 plus B dot V2, V2 dot V2 times V2 plus B dot V3 divided by V3 dot V3 times V3. Okay. Let's just recall what our vectors are for the sake of this calculation. Let's just recall this. So B dot V1, I'm looking at these two, the dot product of those two vectors. We've got 1, -3, -2, 0. Really? 0? Okay. Well, 0 times anything is 0. Okay. Yeah. 1, -3, -2, 0. Yep, okay. Now, B dot V2 is -1, +3, -1, +3, +4, +6. V2 dot V2 is 4. 6/4 times -1, 1, 1, 1. And B dot V3 is 1, 5, 4, 1, 5, 4, 6. V3 dot V3 is 4 times V3. So this is 3/2 times these two vectors added together, V2 and V3. V2 and so I'm keeping my style the same on this line. So I substituted v2. Let's also substitute v3. 1, 1, negative 1, 1. I'm factoring out the constant and then adding the two vectors. So negative 1, adding the first component of both, we get 0, 2, 0, and 2. And then this is, therefore, we don't need this anymore. Let's just delete it. I like to end my solutions with something like, therefore, the projection of B on the subspace W is 0, 3, 0, 3. Boom. Boom. Done. Got it. Got him. Can I... Nope, we don't have the answer in the back of the book, but I feel good about it. I looked up and I double-checked that I applied the theorem correctly. So I'm feeling good about it. I want to just move on. I'm pretty sure that that's right. I could ask ChatGPT, and it probably would give me the exact answer, and do like a good job, like give me a clear explanation. But that's pretty lame. That's super lame, right? Yo, what's up? I see we have a couple people watching. Say hi. Let me know if y'all enjoyed this. Y'all, if you just want to like clap like anonymously, dude, you can just like hit this little heart button. Taps equals claps. That's a thing that some streamers like to say. Taps equals claps. So, thanks. Thanks for watching. Thanks for hanging out with me. Okay. Shall we? Shall we continue? 6.3. I feel like we're getting further into this book. Objectively we are. Okay, 6.3. This section is about orthogonal matrices. I don't remember this theorem that this one is employing. Orthogonal matrices. Verify that the given matrix is orthogonal and find its inverse. Okay, so a matrix A with column vectors v1 through vn is orthogonal if the set vi is orthonormal, which is a damn shame. It's a damn shame that these two terms, that we don't use the same word for both of these terms. I wish that we said that a matrix, that we would call this matrix an orthonormal matrix, because it's a little crazy to say that the columns are orthonormal, therefore it's orthogonal. So you can have orthogonal columns and the matrix is not orthogonal. That sucks. That sucks. I wish somebody would rename everything. Anyways, according to this book, that's the story. So, well, this is part A, and it's very similar. Part A. Matrix A, part A. That's part A, and then... Man, I don't remember. Orthogonal matrices. I believe that an orthogonal matrix satisfy A transpose A equals I. The inverse of an orthogonal matrix is its transpose. I believe that is true, and I'm gonna have to double check myself. We can just calculate it. We can calculate this, and if if this is true, then clearly we found the inverse. So let's see what happens. Let's see if this works. So part A, we do the same thing. v1.v2, v1.v3, v2.v3. So v1.v2 would be 0, 0, 0. Well, yeah. 0, 0, 0. I like to show my work a little bit, like have some kind of work, even if I'm adding 0, 0, 0. v1.v3 is, 12 25ths minus 12 25ths plus 0, and that adds to 0. And then v2.v3, 0 plus 0 plus 0, and that is 0. Therefore, you know what? We're not done. Therefore, vi is orthogonal. vi is orthonormal if each vi is a unit vector. In other words, the dot product of each with itself should be equal to 1. So, if that's true, we can refactor the way that I phrased the definition of an orthonormal basis as vi orthonormal if and only if vi.vj equals 0 if they're distinct, and 1 if I equals j. This would be like a more succinct little definition of an orthonormal basis. vi.vj is either 0 or 1. So we've shown this part for all of the distinct vectors, their dot products that equals 0, but I haven't shown that each of them is a unit vector yet. These are not too bad to do. v1.v1 is 3/5, negative 4/5. Let's copy all this just for convenience over here. So, v1.v1 is 3/5, negative 4/5, 0, dot product with itself. I'm going to just go ahead and do that calculation. This would be 9 25ths plus 16 25ths plus 0. And hey, voila, 9 plus 16 is 25, so this is 1. v2.v2 is 0, 0, 1, and that is 1. v3.v3, again, we have 16 25ths, 9 25ths, and 0. These add to 1. So therefore, therefore, the set VI is orthonormal Give me 1 second. Let's add a new page because I started taking some notes early. Therefore, the set VI is orthonormal, so the matrix having the set VI as columns is orthogonal. So we're done with part A now. Part B, a theorem claims that A transpose, or that A inverse is A transpose. So let's find out if it works. We try calculating A transpose A. So let's remind ourselves this matrix is blue in the top right, 3/5, -4/5, 0, 0, 0, 1, 4/5, 3/5, 0, 4/5, 3/5, 0. And now A transpose, I write rows as columns and columns as rows. So the first row, 3/5, 0, 4/5, becomes the first column. The second row, -4/5, 0, and 3/5. And then the last row, 0, 1, 0. Okay, well, I think that this makes sense to me. Yeah, because I think it's pretty clear to me that this would indeed be a true theorem, because we've already shown that the dot product of each of those vectors with itself is 1. And so those entries lie along the main diagonal, right? And because V1 is the first row of A transpose, and V1 is the first column of the matrix A. So we've already seen that V1 dot V1 equals 1, and V1 dot VJ, V1 dot V2 and V1 dot V3 is 0. So it makes sense to me, yeah, that A inverse would be this other matrix. So we can see that again really quickly. Multiplying rows, dot product of rows with columns. Yep, we get a 1 in the top left, and we get a 0 in this entry. We get 12/5 minus 12/5. This is a 0. Here we get a 0. Here we get a 1. And then here we get a 0. Yep, makes sense. 0, 0, 1. Cool. So therefore, A inverse equals A transpose, which is 3/5, -4/5, 0, 0, 0, 1, 4/5, 3/5, 0. Heck yeah. Heck yeah. So let me know, y'all. Anybody out there watching this? Thank you for hanging out with me. I know that this is very, very niche. I know that this is incredibly nerdy, but dude, I don't know. It's the kind of shit that I would watch if people were doing this. So, thank you for watching. Thank you for hanging out with me. Okay. Let's keep going. So, that was a simple problem from section 3. We're just kind of still working with the definitions. It's not the hardest stuff yet. We'll get there. We'll get to some harder material. Okay. That was section 3. Now let's learn a little bit from section 4 about the projection matrix. I said first thing that we're going to do from section 4 is take some freaking notes on section 4 because I haven't read this section yet. So let's read this section together. At this point, I'm going to turn down my microphone for the most part, turn up the background music, and I hope you all enjoy this math ASMR. So, thanks for watching. That's me. What's up, K-Rimi? K-Rhyme. How are you? What's up, K? Can I call you K? How's it going? Welcome to my practice stream, dude. Hope you're doing well. Oh, hey, Heidi's here. Good to see you. Seriously, it's so cool to me. I don't think, Heidi, that you've ever taken linear algebra, or you're not like a pure math kind of person, but you're just like, you enjoy hanging out and just listening to this. I think that's freaking sick. And yo, you watched my stream in eigenvectors beforehand. It was quite good. I'm happy to hear that. Thank you. Yeah, I'm very optimistic, cautiously optimistic that this stream, has like more replayability. It's a little more evergreen and, potentially more interesting than my guitar content. I'm very proud of my guitar content. I'm a guitar YouTuber as well. This is my music that we're listening to clearly in the background. But yeah, people seem to be enjoying the math streams. K Remy, is this your first time joining live? Dude, it's fun. It's good vibes. I try to create like a welcoming kind of vibe. Thanks for hanging out, Heidi. All right, so we've got some projection matrices. This is your first time joining? Heck yeah, heck yeah. That's great. Well, thanks for being here. Okay. That's always kind of bothers me. What color should the outside be of these boxes? I don't like that we have yellow and yellow, but I always want to add like a third separate color. But then I'm like, well, which one? I mean, I'm getting distracted by the stupidest stuff. Yeah, I don't like a third color. Let's start getting used to two color boxes. I think. I don't know. You all tell me what looks nicer. dude, Kairami. K. How do I pronounce your name? Is it Kairami? Kairime? Dude, if it's your first time joining, welcome. Welcome to the stream. Tell me a little bit more about yourself. Are you a math person? Are you interested in learning? Kairime. Okay, heck yeah. Thank you. Thank you. Are you a math person? Are you like studying linear algebra? Are you in high school? Are you in college? You enjoy maths. Nice. Yeah, me too, man. Obviously. Obviously I do. Okay, cool. That's all of the notes from this section. So my colorful boxes are getting a little less colorful. I'm just like going back and forth between yellow and blue. I think that's okay. Oh, you're in the UK. Nice. Nice, dude. I'm tempted to just write everything in white and just do like black and white, like very Luna and Kaya style. But that's just like a little too intense, I feel. But it would be a little more like a blackboard, like a chalkboard, if I'm just writing everything in white. Okay, cool. So I'm done taking notes now on this section. I read the section and I took notes. Done. Now we're going to work this problem. Whoops, oops. Why am I struggling? All right. Here we go. I'm really struggling. Cool, you're in the UK. Nice. Are you in high school or college? Or what's your deal, dude? Okay, so I learned a little bit. Let's try to work this problem. Solution. Let's get this into muscle memory. P is A transpose A inverse A transpose, right? Where A is 2, 1, negative 1. Because there's only one vector, v1. And we write A is the matrix of column vectors for the column space of that set or something. So let's find A transpose So A transpose is, we write rows as columns and columns as rows. 2, 1, negative 1. A transpose times A. First off, I notice the set V1 is not, well, it's not orthonormal. I mean, it would be orthogonal, I guess. I guess it's orthogonal. I guess it's orthogonal. We could normalize it. Okay, we're going to do two solutions. This is solution 1, the direct approach. You do A levels, which I think compares to last year of high school. Nice, nice, nice. Have you ever seen linear algebra like this? Like working with matrices, but like more complex theoretical questions about matrices? Like, do you know what a vector space is or a linear transformation? Dude, this to me is when math starts getting like really, really cool. It starts getting abstract. Okay, so we're going to do two solutions to this problem. One of them is going to be the direct definition approach. 2, 1, and then we're going to have a more clever argument after. So, well, A transpose A is just going to be the dot product of that row with that column, which is 4, 5, 6. So it's a matrix with only one entry, 6. The inverse of this matrix would be the matrix 1/6. I mean, it's like you can kind of think of it like a number, but it's a matrix with one row and one column. Then A transpose A inverse times A transpose. I'm just going to jump right to the meat and potatoes of this one. Now we have the matrix A, again, was 2, 1, -1. A transpose A inverse is a 1x1 matrix, 1/6. And A transpose is a vector. Something feels off, but maybe not. 2, 1, -1. So we multiply the second and third matrices together. So 1/6 dot product with 2 is 1/3. 1/6 dot product with 1 is 1/6. 1/6 dot product with -1 is -1/6. And now 2 dot product with 1/3 is 2/3. This would be a column vector, won't it? Oh wait, what the hell is this? No. This is going to be a 3x3. 2 dot product with 1/3 is 2/3. 2 dot product with 1/6 is 1/3. 2 dot product with -1/6 is -1/3. 1 dot product with 1/3. Let's simplify our lives a little bit. Why are we working with thirds so much? Let's factor out 1/3 out of the rightmost matrix. Oh, no. Slow down, John. Let's factor out 1/6 out of that matrix. So then we have 2, 1, -1. And, well, now we're getting to 1/6 times 2 times 2 is 4, 2 times 1 is 2, 2 times -1 is -2. 1 times 2 is 2, 1 times 1 is 1, 1 times -1 is -1, -1 times 2, -1, +1. So, our final matrix I'm going to say, therefore, our projection matrix is 2/3, 1/3, -1/3. Ooh, you know about a vector space, but you haven't studied it in school. Nice, dude. Nice. But now you know what it is. Maybe partially thanks to my videos, right? Come on. Yeah. Well, it's nice to have you in the community, dude. Thanks for being in the chat today. I hope you're enjoying the videos. What do you want to see out of this channel? I mean, this is still a pretty new channel overall, dude. This is still a pretty new channel, and I think that it could be really cool if I can find out what you all, want to see. Like, I want to study math. How can I make that interesting? you know? Like, how can I make that interesting? How can I, like, study and make that fun and interesting? So the projection of B on W is PB, not peanut butter, but PB. I'm going to keep out that 1/6. So, you know what? P can be written with that factoring. And our vector B, let's go back to the original question. Our vector B is 1, 2, 1. We'll keep out that 1/6 factor. And then 4 plus 4 minus 2 is 6. 2, 4, 3. -2, 0, 1. So B, the projection of B on the subspace is found by 1, 1/2, and 1/6. Boom. Cool. It seems like a lot of work this time around compared to solution 2, which I'm about to do. Let's try solution 2. B, the projection of B on the subspace W is the projection of B on the orthogonal vectors, and there's only one orthogonal vector, so in this case, we should see that these two match. We'll see. Does it? Hopefully. What is B dot V1? Recall that B is 1, 2, 1, and our only basis vector is 2, 1, -1. 2, 1, -1. So then B dot product with V1, we multiply corresponding components and then add everything together. 2, 4, 3. 2, 4, 3. Yeah. V1 dot V1 is 4, 5, 6. 6. V is, again, or V1 is 2, 1, negative 1. So this is 1/2 times 2, 1, negative 1. And we claim that BW is 1, 1/2, negative 1/2. Dude, is that what I wrote down earlier? That doesn't sound... 1, 1/2, negative 1/2. That's not the same. Did I do an oopsie on the math here? Negative 2 plus 2 plus 1. Did I do an oopsie somewhere? B dot V1 is 2, 4, 3. Yep. V1 dot V1 is 4, 5, 6. Yep. And then times V1. What happened? Because that doesn't match that. So let's double check our work. This was a lot of work to do it the other way, the way that this chapter introduces. So I'm not sold yet on the benefits, but I know it becomes easier in general. I mean, if we can find a matrix that works for any vector, then that's quite useful. Like if we have a lot of vectors that we're going to calculate, then we don't have to do solution 2 for every individual vector. 2, 1, negative 1. So our matrix is 2, 1, negative 1. I wrote that correctly. A transpose will be 2, 1, negative 1. That's written correctly. A transpose times A, 4, 5, 6, yep. And A transpose A inverse is 1/6. Oh, wait, no. 1/6 times 2. 1/6 times 1. What went wrong? 2 dot product, or 2 times 2 is 4. 2 times 1 is 2. 2 times negative 1 is negative 2. 1 times 2, 1 times 1, 1 times negative 1. Negative, oh, here we go. Oh, wait, no. Negative 2, negative 1, positive 1. Okay, I did that fine. I factored in, and then I factored out again, so let's, 4, 2, negative 2, 2, 1, negative 1, negative 2, negative 1, 1, times the vector 1, 2, 1. What went wrong? 4, 8, 6. So the first entry is correct. 2, 4, 3. That's correct. 2. Oh, wait. Negative 2 minus 4. It's right here. Oops. I did make an oopsie. Okay. That should be negative 2 minus 2 plus 1. Negative 3. Yep. Okay, I knew that there was a mistake in here somewhere. Okay. So this last entry actually should be negative 1/2. And then this calculation matches our old way of finding these projections. So, okay, cool. Done with that problem. Haven't yet seen why this is super cool. Because we did a lot more work than the old way. But we will see next time, like, these problems are going to get harder, and we will see that this approach of finding a projection matrix simplifies computations a bunch. So that's interesting. I look forward to that. Cool. Hey, we got a few people watching. We got 3 freaking nerds out there on the internet. We got 3 nerds watching another nerd practice math live. We got a whole party of nerds over here. Thank you for nerding out with me, everybody. Please hit the like and subscribe before you go, and let me know what you would like to see out of this channel. Anyone want to hear a guitar song? Let's pause. Let's take a break. Let me play you all some music. We got a beautiful theorem. This is the most beautiful theorem that we've written today. Can I play you all some music, dude? Okay. So I don't know who's heard classical guitar before and who hasn't heard classical guitar, but I love it. I mean, it's a very different style of music. It's a very different style of guitar than what most people have heard before. So these are all my channel supporters on my other channel. If y'all are interested, it's pretty good vibes over there. Like, Heidi is hanging out here, just lurking, just enjoying some math, and she's not even a math person as far as I'm aware. And she's a regular in the guitar channel. So if y'all are ever curious about that, there's my guitar channel. Would love to see you in the chat sometimes. I do the reverse over there. So over here, I use my guitar as background content, and then over there, I use my math as background content. So, you know, neither of these hobbies is more important to me than the other. I truly freaking love guitar and math. And it's just nice to be able to practice with an audience and everything and try to build a community around it. So let's play some Bach. Every time I'm studying math and I play music for you all, I just want to play Bach, because Bach is like the most mathematical, elegant, crystalline, structured, beautiful guitar music, or really music in general. So I hope you all enjoy this. Here's the prelude from the first cello suite by Johann Sebastian Bach. I also like to just call it that one cello song, so I hope you enjoy. surprise little bit of crossover content of classical guitar on the math stream. I'm practicing this piece on the piano. That's awesome, dude. That's awesome. So you are a fellow math and music person. It is a real thing, right? Isn't it a real thing that like a lot of musicians are also interested in math and vice versa? Like pretty much every mathematician I know also is into music. Not always the reverse. I know a lot of musicians who are not math people and they say that they don't like math. I'm like, you're missing out, man. It's so similar. It's so, you know, it's equally beautiful, I think, for a lot of people, math and music. It is for me. All right. Thanks. I hope you enjoyed that, y'all. Thank you. Thank you for indulging me, I should say. Thank you for indulging me. Okay. How much? We're an hour and a half into the stream. I think I just want to take notes on the last section. Let's just take notes and see if we can call it a day after that. So we got the method of least squares. Hope you all enjoyed. And let's get the background music going again. Let's play a different background music because I have a whole other recital that I've recorded. That's a good one. Recently. A recent recital. Woo, that's too big. That's far too big. That's me. This is one way to try to get people to watch my guitar content. Dude, this is one way. I don't know if it's the best way, but this is one way to get some eyeballs on my guitar content. Okay. Thanks for watching. Let's keep practicing. So let's take a short break. Okay, I'm back. Let's keep going. All right, so we got rabbits populating a large island. We got a table of data here. Oh, those pesky rabbits. Pesky rabbits. The method of least squares. Am I going to get all the way through this section today? Or should I just read it and read it privately and get like the most important parts? I'm not gonna take detailed notes this time around. There's kind of a lot in this. I don't think we're not gonna get to all of this today. But we can definitely get the most important parts. And I wrote down some problems that motivate this section. Isn't it better working work orthogonally with like orthogonal errors rather than Okay. I think I generally get this idea. Okay. I think that's it for today. We landed in a good place. We got to defining the problem and at least writing down this least square solution process for these problems. So thank you everybody for joining me, for studying linear algebra with me. It's been a pleasure. This is some of the most useful math in the world, especially this section. So next time, I hope that we can actually work this first problem about springs and like measurements about attaching weights to springs. All right. Thanks everyone for watching. I'm going to go. Bye. I hope you enjoyed. Like and subscribe. Thanks for watching. Bye.